All right.
Sometimes people do that, sometimes people do.
Great. Well, thank you everybody for coming to this seminar, which is co-sponsored by the Department of Environmental Occupational Health, the Urban Health Collaborative, and I wrote it down because I want to make sure I get the name right, the Drexel Climate Change and Urban Health Research Center. Yeah. So we're so happy. This was sort of a last minute seminar situation, but like super exciting, and sometimes the best ones happen this way. But I feel like many of us know Tarik Benmarhnia because he's visited at least twice before. So Tarik is an associate professor at the Scripps Institute of Oceanography Department at UCSD, and he is the director. He runs the climate epidemiology lab there. And I have to say, so I know we're not supposed to have favorites, but Tarik is one of my absolute favorite environmental epidemiologists because he does this amazing job of bridging the worlds of social epi, environmental epi, and he's a really, really good methodologist. He's super smart. I shouldn't advertise that because then everybody might dog you. But he's also extremely collaborative, and he has helped me a lot over the years. So it's just an absolute pleasure to have you. So thank you for being here.
Is it better if I sit or stand up? What do you do usually? Okay, can you make sure they hear me correctly? I don't have a very loud voice. So just to make sure they can hear me, I can say.
Yes.
Thank you, Leah. Great introduction. So yeah, thank you everyone. Nice to meet most of you. Nice to see people that I met before many times. So okay, so I today I just wanted to give you just like some context about this presentation because it was a last minute thing because I was visiting New York City the last minute and I reached out to Sam and said, hey, I will be on the East Coast and Philadelphia is not very far based on my geographical understanding. So shall we meet? So I organized that. So I was about to recycle the presentation that I gave a few weeks ago in LA. But then when I was working on that, it was boring to go through a presentation again. So I put together a new presentation on 3 new papers that we're doing just about just like how the effect of wildfire smoke, PM2.5 specifically on mostly respiratory health varies. So on space and in relation to extreme heat. And the last one is also just about more methodological work about how we can use different types of synthetic control methods to analyze the effect of wildfire smoke. And so that's what I will talk about today. Yeah. And I started to work on wildfires when I moved to California for obvious reasons, but now it's an East Coast problem as well, as you noticed a few months ago. So I wanted to give you just a brief introduction about wildfires, smoke in the context of climate change, and I will talk about California because this is where most of our work is based. And also, I will give you just a short story about why we see more and more wildfire, specifically in the fall in Southern California in the context of climate change. And just to give you an intuition about the links between climate change and wildfire regimes and why this is very sneaky. This is very complex. It's not like a kind of atmospheric moisture or temperature. It's not a very simple story. And then I will talk about 3 different papers. The first one will be just about how we explore the spatial heterogeneity and the health effect of wildfire smoke PM2.5, and I will explain how one approach about how we can model exposure to wildfire smoke PM2.5 in a given location, in an census tract, for example. And then we did that at the county air basin level and at the zip code level, and we also tried to understand what kind of zip code characteristics in terms of population composition, socio-demographic characteristics, etc., modulate this effect. So this morning, this early afternoon, we talked a lot about effect modification and this kind of synergistic compound impact between social and environmental factors. So this is a lot about that. So the second paper that I will talk about is a paper that is still a revision, but this is but there is a preprint, if you're interested. But we explored the synergistic impact between wildfire smoke PM2.5 and extreme heat in California. and try to understand like the small scale variability. So I will explain very briefly methodologically how we did that, but that was an extension of some approaches that we used before. And I think the last time I talked, it was during COVID, so it was virtual, but I talked about what we did in terms of extreme heat and ozone. So we just expanded that to extreme heat and wildfire because that's very comparable, analytically speaking. And finally, I will talk about how like we can just like expand like I don't know if you follow the literature on the quasi-experimental methods that are based on the timing of an intervention, like, and there is a lot of development in a diff literature based on staggered intervention. And this is a very active area of research. If you follow this literature, this is very, very hard because every week there is a new paper. But so what we wanted to do here is to adapt this method in context of a synthetic control methodology to analyze like the heterogeneous effect of a wildfire smoke event. So we took the 2018 campfire as an example, and here this example, this is how we can, this is just to show you how we can use this type of kind of capitalization of a wildfire smoke event in a given place in a given day as a natural experiment and see how we can explore the heterogeneity of a space, but we can do that over time, etc. So there is a lot of extension, but I just wanted to take this opportunity to talk about how we can use synthetic control methods, specifically extensions of that generalized synthetic control method to understand just like the impact of wildfire on health and their heterogeneity. So that's the menu for today. So, okay. So this time I'm watching because I'm very bad at keeping time. So first, just about some background. So you probably already saw that if you attended the talk on wildfire and health, there is always something about that. But on our right side, this is just like very obvious picture about. So it's like this is in California. This is from Cal Fire, and we can see here this is the 20 largest California wildfires since we record them, like more than 1 century ago. And you can see here like a very, very clear and unambiguous pattern about the fact that the largest and more extensive fire took place in the last decade, and especially in the last 5 years. And this is not a coincidence, it's not random. So this is the first pattern, so this is obvious, and you saw that everywhere. But one thing that I think is a little bit less known, but still interesting to understand why we see that, is what you can see on the left. Because you can see an increase in a surface and a kind of intensity of this fire, but you can also see a change in the seasonality. And this is what is very specific to what's happening in the Western US, but specifically in California. We see like most of the largest wildfires are actually taking place more and more in the fall. So between October and December. This is why it's becoming the wildfire season. And we'll explain why. And this is just why this is also kind of not or directly or indirectly linked to anthropogenic climate change. So that's, and also something, so we'll talk about one type of fire regime because there are different types of fire regimes. So I will talk about the kind of the non-forest fires. So the fires that, for example, take place in Southern California or the one that takes place in Northern California. But you also have different types of fire regimes, mostly the forest fires that take place in Yosemite also, that have a different pattern. They usually, the seasonality is a little bit different and usually take place in the summer and are mostly driven by very hot temperature and long period of drought. So it's two different fire regimes. This is what we have in the Western US and specifically in California. So we just talk about one type of fire regime, just to say that there is a lot of heterogeneity in the types of fires, and it's very complex. You really, so I know very well what's going on in California, but even in Oregon, I have no idea what's going on, and even less in Canada. So this is just like a disclaimer, I will just focus on one type of fire regime. So there are two reasons actually for which we see an increase in intensity and also concentration of this wildfire in Southern California taking place in the fall, and especially in the last few years. That's the same thing in Northern California. So the first component is what we call a change in precipitation regime. So precipitation regime is just like how precipitation is distributed in a given year. So here on a figure on the bottom, this is from a paper from a few years ago from some colleagues at Scripps, just comparing the different types of Mediterranean climates around the globe. So California, South Africa, Australia, Chile, and the Mediterranean region. And here you can see that overall, you have a decrease in the type of precipitation events in all of this Mediterranean region. But in California, it's very special because there is a kind of overall the average annual precipitation amount stays the same, but it's a kind of anomaly because on one hand, there is a reduction in a kind of not extreme events, but on the other hand, there is an increase in one specific type of extreme weather events and precipitation events, which is driven by atmospheric rivers, which are just a very specific type of precipitation regime that is exacerbated in the context of climate change because we just like it's driven by a lot of moisture in the atmosphere. And as you know, if one of these like with global warming, there is just more moisture in the air because the ocean is just like spreading more humidity. So these atmospheric rivers have, for reasons that will take some time to explain, but just they have what is important here is that they have a very, very strong seasonality. So they don't take place all year long. They really take place between January and March. And they are very extreme. I don't know if some of you are from California. I don't know if you experienced the atmospheric river. This is just like when it's flooded and when you know that California don't know how to drive when it's raining. And this is just like very intense. And this is very special. It typically happens in the winter. And that is the first component. So on one hand, we have less precipitation from normal regime, like non-extreme events. But on the other hand, this is compensated by these very, very extreme events that have a very strong seasonality. So that's very important because then we have not a lot of rain usually, but in the winter, you have this very, very huge amount of rain, and after that, nothing. Long period of drought is followed by the summer. And then at the summer, you have the vegetation that is like flourishing, but then it's ready to be just like super dry because it's very hot, because there is a change in the temperature distribution as well. But at the end of the summer, you have huge amount of vegetation because of this extreme precipitation taking place in the winter. So at the end of the summer, typically, you have a lot of dry vegetation that is just ready to burn. So that's the first component. The second component is one thing that is very specific to California, and it is type of downslope wind. So in Southern California, we have the Santa Ana winds. In Northern California, they have the Diablo winds. So this is very specific, and this is driven by the Sierra Nevada. So we have, this is like very strong winds that you can't miss when they happen. They are very hot and very dry. And they are typically from the east to the west. And this type of downslope wind have a very, very strong seasonality, and they typically start in September. So, and Santa Ana winds are very bad for wildfire because on one hand, they trigger them because the main reason for which large wildfire started because of electrical cables that is falling on the ground. And if it falls on the ground with a lot of vegetation that is dry, it starts, but then it spreads the fire. And on top of that, once there is a smoke, all of the smoke goes to the coast. So this is just like the only reason for which we see this huge, this increase in intensity and surface, this wildfire with concentrated in the fall, typically these days, is because of these two conditions. So if the precipitation regime was not the same, if it was, for example, raining a little bit later or a little bit earlier, or if the Santa Ana had a different seasonality, we would not see this huge wildfire for this type of fire regime. So this is just to explain just very briefly why, in the context of climate change, we see this increase in these types of wildfire in Southern California. And this is very comparable to what's happening in Northern California because of the Diablo winds that have a very similar seasonality and are very, very similar winds. But it's just to give you an intuition about why we see more and more wildfires for this type of fire. So just an introduction about why this is a big issue. On top of that, so now I will focus on the smoke because, of course, when you look at, when you study communities that will be directly impacted or exposed to the wildfires, this is a big deal because you have, first of all, a lot of pollutants, direct pollutants, including, and the most problematic one is carbon monoxide, CO, which is associated with a lot of issues, including planetary mortality and intoxication. And you also have a lot of chemicals that will be generated from the burning of built environment. And also just all of the consequences in terms of food insecurity, in terms of economic insecurity, if you lose your house, etc., and the mental health consequences. But here, this is what we call the direct impact, which will eventually impact a very small number of individuals at the end of the day, because in this context, most of the fires are taking place in the east, very rural, very little, very small populations. But then the problem, and this is what I will focus on today, is the smoke. the smoke once generated can be transported over a long distance. The fires, like the smoke you had a few months ago, were coming from, I don't know, maybe like 1,000 miles ago, away from here. So it can travel a very, very long, very long distances. So one of the main metrics that we use to capture exposure to smoke is PM2.5 fine particles, which is just like one of the key components of smoke. It's not the only one, because when there is, we talked as well about that this morning, when there is like smoke, PM2.5 is the main component. This is what we study mostly, but it's not the only one. There is also a lot of evidence about different types of PAH and ozone as well as a gas that is also exacerbating context of wildfire smoke. But today we just mostly talk about PM2.5. So the reason for which we focus on that is that the smoke is transported to the west, and in California, at least, most of the population is on the coast. So this is, at the end of the day, there will be millions and millions of individuals that will be exposed to the smoke, to this additional level of PM2.5 that can reach very, very high levels of exposure. And so the first problem is that in California, at least, or in the Western US in general, now air pollution is becoming a wildfire smoke problem. So wildfire smoke is the main contributor of PM2.5 exposure in California nowadays. And here you can see just a paper from 2018, just showing how in the future, using different types of climate generalized circulation model, try to project the kind of the contribution on non-fire versus fire PM in a total mix of PM. You see that more and more, most PM are going to be generated by wildfire smoke. And this is, I don't know if you saw this study from a few months ago, I think now, published in Nature, just showing how, because of wildfire smoke, it's just like all of the benefits due to the Cleaner Act and different types of air quality policies were in the Western US were basically canceled, kind of eliminated because of the huge increase in wildfire smoke PM2.5. So just to say that in the Western US, and especially in Oregon, Washington, and California, we can see that all of the benefits are being canceled, and air pollution is becoming a wildfire smoke problem. So of course there is a very strong seasonality, but this is like the summer, you have the forest fires that can reach the coast, but you have mostly this kind of fall, early winter, downslope wind driven wildfire. So this is just to say that that's the first problem with wildfire. This is like the main contributor of PM2.5 in the Western US, and it's changing in the Eastern US. So that's just like the first component. The second component is about the specific health impacts. So we use the same figure. So of course, when we look at PM2.5 total mass, there were a lot of evidence for like PM2.5 generated by any source about the health impacts on an acute way and on a chronic way, including inflammation, including oxidative stress, including like the alteration of the immune system, and especially the macrophages in the lungs, etc. So there is a lot of evidence on PM2.5. And when we try to study the impact of wildfire smoke PM2.5, one question is, do we see the same risk? Do we observe the same toxicity when PM2.5 is generated by wildfires as compared and transported to the smoke as compared to PM2.5 generated by other sources of emission, including traffic or agricultural activities, etc. So there is some evidence from the toxicological literature related to wood burning showing that for this, like the dose response is not the same. And studies from 10 years ago, more or less, showed that the dose response was up to 10 times higher when PM was generated by wood burning as compared to traffic exhaustion, typically. So one thing that we wanted to test a few years ago was, do we see the same pattern in human population, epidemiologically speaking? So when we disentangle the concentration of PM2.5 coming from wildfire smoke and PM2.5 coming from other sources, do we see the same dose response? Yes or no? And the answer is no. And this is just very quickly from a paper published a few years ago, just showing how we compared different methods, and later I will focus on one specific method just to give you an idea and intuition about how we can isolate PM2.5 coming from wildfire smoke from other sources of emission. But we did here, and we compared different approaches, including an instrumental variable approach, an imputation approach that we'll describe later, an approach based on interaction, and an approach based on seasonal interpolation, which is, for example, what another another team modeled by Marisa Childs and colleagues. They modeled they developed a product, statistical product for wildfire. They use this type of seasonal interpolation coupled with dispersion models. So here, the main point is we compare that, and here you can see if we focus on the imputation, I don't know if you can see, but this is just like if you look at this number, you can see that for the same increase in the dose in exposure to PM2.5, the response was up to 10 times higher in terms of respiratory hospital admission in Southern California. And we replicated that using different methods in different outcomes, different population, different region, and we always found the same pattern between 3 and 10 times higher. So, which is also consistent with what we see on the toxicological literature. I don't know if you saw a few days ago, there was this paper about coal and showing that the PM2.5 generated by coal was up to 3 times more toxic, more like the dose response was higher as compared to traditional sources. So this is just like not the same amplitude, but this is the same idea, the same story, just about how PM2.5 total mass is being criticized more and more as a proxy for or as an exposure because there is so much heterogeneity. And when we look at that, and especially given what I just said before, the fact that now wildfire smoke PM2.5 is becoming the main source of emission, we can't assume that this is equal, exchangeable with traffic-related emissions. So this is why this is important to try to understand this impact. So anyway, just big intro. Okay, not that bad. So now, and actually, this is also just like an extension of this work that we did, just to show here what we did. We just did like a kind of compared what we call the naive approach. We did a health impact assessment to quantify the total burden, the total number of hospital admissions attributable to PM2.5. And we compared one naive approach in which we did as done typically, where we have one dose response, any type of PM2.5, and we quantified the total number of hospital admissions attributable to PM2.5. And then we did what we call the nuanced approach, where we compared like the exposure to PM2.5 according to wildfire or not, and a specific dose response. And here, this is just a visualization, like a map of the delta between the two approaches. So the nuanced minus the naive. And here you can see that, especially now in Northern California, you actually miss a vast majority of the burden. I think I forgot the number, but I think it was something like 30%. So 30% of the burden is missed if you don't consider specifically those response that is specific to wildfire smoke. So this is what we also wanted to show in this paper. So this is relevant for wildfire smoke, but this is also relevant for other sources of emission like coal. So anyway, so now I will just go more specific in showing some case studies. But just like the big picture is that in the literature, we'll find 2 types of studies trying to link wildfire smoke exposure and health outcomes. You have papers, studies that focused on specific large wildfire events. For example, you have a lot of examples from the 2007 event in San Diego. You have like a lot of papers about what happened in Russia in 2010. There was a lilac fire in San Diego. There was a camp fire in California, and I will take example for that. But, and that is, this type of study it's practical because you don't need a lot of effort on a wildfire smoke modeling, because you can try to identify when the fire started and when it stopped, and you can just use simple satellite imagery to identify when it started, and you have a lot of products that are available. I don't have any slides about the specific fire product, but if you have any question, this is the US is actually very progressive in terms of products that are available to study wildfire smoke and smoke specifically, as compared to other countries. But there are a lot of available products. In California, we have a lot of information about the fire parameters, about what was burning. We also have the HMS product, the hazard mapping system product from the NOAA, which is like validated by experts, just like where on a given day the smoke is and is going. And if this is smoke adjacent to other, just like reason for which we may see some kind of like smoke in a given place. So I will give you an example about how we can model it later. But you can also be interested by studying long time periods. But to do that, you really need to model daily wildfire smoke PM2.5. And to do that, you have 2 big families, like approaches based on dynamical approaches, could be based on chemical transport model, and there are different existing models for that. And the most commonly used. One is the geoscam, but you also have WALF, for example, which is another type of chemical transporter that could be useful. You also have dispersion models, and the most common one for this in this field is high split. And this is dynamical approaches, mathematical models that could be useful to model that. Based on a lot of assumptions, there are advantages, but not only. Another alternative is based on statistical approaches. And I will talk about one approach just to give you an idea, but the same thing, this is to me a little bit easier based on my background, but also this is easier, especially when you want to, if you want to do like a very large study area across many years, this is more realistic because you don't need the same computational powers as compared to a geoscam, for example, that is very, very demanding. So, okay, so the first paper I wanted to talk about, very simple idea, just we wanted to understand like across 15 years of data. So we modeled wildfire smoke PM2.5 daily for each zip code. And we wanted to see if there is some spatial heterogeneity in those response modeled as, for example, odds ratio. And we did that at 3 levels. We did that at the county level. We have 58 counties in California. We also did that at the air basin, which is a geographical, I don't even know if this how it works in Pennsylvania, but it's probably the same. You have probably air basins that are responsible of implementing the air pollution, national air quality guidelines, right? I don't know about Pennsylvania, but I don't know. But in California, we have 15 air basins, and each air basin has the responsible of implementing and monitoring air pollution, and so we also we did that, and this is what I will focus on. But we also did that at the zip code level, and at the zip code level, we also have all of this socio-demographic information. So then we wanted to understand what characteristics drive this heterogeneity at the zip code level, and I will show you a result about that. So this is what we wanted to do. So, oh yeah, I already said that. So, but this is, we used like for the county and air basin analysis, we simply use a stratified, time stratified case crossover. So we just ran a case crossover analysis for each county or each air basin. But for the zip code level, we use a kind of extension of, you can see that as an extension of a case crossover, but a spatial extension that is a Bayesian hierarchical model coupled with a community match design, and I will describe that later. But this is what we used in a heat and ozone paper that we presented last time. But here we just extended that to wildfire specifically. But I will talk about that for the wildfire heat because this is a good technique to capitalize with the spatial structure and also couple that with a Bayesian framework to be as efficient as possible for the estimation of the variance. And then once we did that specifically at the zip code level, we wanted to understand which socio-demographic characteristics in terms of, for example, race, ethnic composition, unemployment, etc., was driving the potential heterogeneity. And we use a random effect meta regression to do that. So, okay. So here, just to give you very quickly an idea about how this is one approach among many about how we can, but I think this is the most intuitive one, but this is how we can actually quantify daily wildfire smoke PM2.5 in a given area, like the census tract, the zip code. So this is like a 4-step process. So the first step is to use like just like a model to predict PM2.5, predict and optimize and validate PM2.5 exposure for total, like all sources of emission. So now the state of the art is to use what we call an ensemble model, which is going to be like a kind of hybrid land use regression model that will combine a lot of predictors, including meteorological factors, land use characteristics, including traffic, etc., but also green spaces, etc. And then the idea of an ensemble model is to combine multiple machine learning algorithms that will be that will capitalize on cross-validation. But the idea of an ensemble model, which is equivalent to a superlearner, just to use multiple machine learning algorithm and just like to weight different types of algorithm according to their performance in a given county, for example, in a given zip code, in a given region, or in a given season. So just like said simply that you can have a very good machine learning algorithm that works for San Diego in the winter, but maybe it fails terribly in the summer. So you want to use maybe deep learning in the summer. I don't know, I'm making that up. But this is the idea of an ensemble model, just to try to combine different types of algorithms and so just to be as flexible as possible. So we do that, we optimize that, and then once we are happy with our model to predict total PM2.5 at the zip code level, at the daily level, then we move to the second step. The second step is going to try to identify for each day where the smoke is, and if there is the presence of smoke that is at the surface level in a given zip code, for example. So to do that, so we use multiple predictors, but a very important one is HMS, which is based on satellite imagery. And this is also just so we really can know to which extent there is, and this is combined with some observation on the site, just to make sure that if there is smoke on a given day at the surface level that population will be exposed to. And so this project started in 2006, and since 2010, there is also 3 levels you have of the smoke density. So you can also modulate the intensity of the smoke. So we use that to understand to which extent there is some smoke on a given day in a given zip code. So the third step is simple. We just, in this time series data, where we have all of the days and all of the zip codes also subtract, you just replace this days zip code where you have the presence of a smoke that is validated by missing data. So you just replace that by missing, as if you didn't know. And then you're going to do a spatial temporal multiple imputation approach. So you're just going to predict what would be the expected level of PM2.5 using information from the days before, so the days after, from the years before, and the surrounding zip code that were not exposed to the smoke, to try to impute the level of PM2.5 that would be expected in the absence of the smoke. And finally, you can simply compare what you imputed to what you actually observed, and you can attribute this difference to the quantity that is attributable to wildfire smoke. So this is one approach that we can use to quantify wildfire smoke PM2.5. This is the most intuitive one. And this is what we can use. And this is what we actually use in this paper to actually know on a given day, in a given zip code, how much wildfire smoke PM2.5 was exactly there. And yeah, and there are some limitations, of course, because, for example, when there is very, very high level, we won't get that because a predictive model can't predict things that for which data has not been trained of. So when you have days that reach 350, you won't get it. So this is, but there are many other assumptions, but this is just to give you an intuition. So this is just an example of what we found at the air basin level. So you can see the 15 air basin, and here you can see that this is the higher effect in relation to the similar increase in terms of, I think it was a 10-unit increase of wildfire smoke PM2.5, so the contrast. The highest effect estimate on a relative scale is in San Diego County. And you can see that there is a substantial heterogeneity across air basin, which is useful for policy-wise, because this is really just to show that you have some air basin that really should prioritize just what to do and how to adapt the specific guidelines in relation to PM2.5, where other basins don't necessarily have to be too much worried in terms of the effect estimates for their populations. But we also did the same at the zip code level, and here this is what we found in terms of what zip code level characteristics modulate this effect estimate. So for example, we distinguish race ethnicity variables from socioeconomical variables. And you can see, for example, the first line, the percentage of Black individuals, non-Hispanic Black individuals in a given zip code exacerbate the health effect associated with wildfire smoke. It just means that the higher the proportion of people self-reporting being non-Hispanic Black, the higher the dose response it will be in terms of wildfire smoke PM2.5 and respiratory hospital admissions, and so on. And we found, for example, that of course air conditioning was a predictive factor, etc. So this is just what we wanted to do to understand the sources of variability in terms at the zip code level in terms of susceptibility to wildfire smoke PM2.5. So that was the first paper that just to show you how we can try to understand the heterogeneity of just wildfire smoke PM2.5. The second paper is instead about the compounded impact, and so here the question was, see when there is at the same time a wildfire smoke event in a given zip code and an extreme heat event, depending on different types of extreme heat conditions, do we see a synergistic effect? And do we see, for example, does the effect of both is different from the sum of the both effects, basically? So, and we focus on an additive deviation from, on an additive interaction scale for this reason, because this is what we wanted to see, where the highest burden was happening. But this was a question of this paper, just to try to understand that, and also something, because it's something we typically do, what is driving this synergistic effect? So what factors are correlated with a systematic increase in the joint effect of wildfire smoke and extreme heat at the zip code level? So yeah, so that's just like a very simple visualization about the spatial distribution of the total number of days with both extreme heat, with one definition of heat just for simplicity, but we compare different types of heat definitions. Same thing for a smoke wave, we define different type of binary smoke wave definition, but this is just like one example of the spatial distribution of where both are happening. Then it's just like the number of days with extreme heat alone with one specific definition, and then the total number of days with just wildfire alone. So what we want you to do is to understand just like this synergistic impact, but at the zip code level. But because it's, we have to be very, and we can't waste a lot of data because precision-wise, because we really want to get area I, which is an estimate to calculate deviation from additivity at the zip code level. So we really want to get that. So one thing that we did, and this is here's the approach, is to use this kind of spatial extension. We can see that as a spatial extension of case possible. We call that within community match design. So the idea basically is to find for a given zip code, a given day with like, that is, for example, exposed to both extreme heat and wildfire. Then we're going to take all of the days that are not exposed to neither of that. So like if you look at the formula of the like area wide, it will be the R00. So when you're not exposed to neither extreme heat, no wildfire. So for the exposed day, you're going to take to both, you're going to calculate the number of the rate of the number of hospitalization, for example, for a given cause. And you're going to calculate the same number or the rate for all of the control days, 0, 0. And you can, what we did here, we took a time window plus 30 days and minus 30 days. And what we did, we just simply applied the weighting procedure. So we gave more or less weight according to the distance of the control days to the event day. And we did that for all of the days. So we did that for all of the like risk for 1-1. So when you have both extreme heat and both wildfire. We did the same when you only have wildfire. We did the same when you only have extreme heat. And we did that for each zip code. So for each zip code, you can actually get like an average difference between each of these conditions and none of them. And you can, using that, you can estimate like an area I, which is just like the risk of both minus the risk of just one, minus the risk of just the other one, plus one. And that gives you the estimation of additive interaction. That is area I. And so this is just like the overall approach, but then we need to estimate the statistical, like we need to do some statistical inference. So the reason for which we used a Bayesian hierarchical model to couple with community within community match design is to address two problems. The first one is a spatial autocorrelation, because there is a lot of reasons to think that the area in two like zip codes that are in the same area are going to be similar. So we want to capitalize on this information and to deal with spatial confounding. So that's the first reason. That's usually the main reason for which we want to use spatial models. But another reason is also to be more effective to estimate the precision. So instead, if you focus on a kind of traditional kind of statistical testing, parametric statistical testing estimate, you would, each time you would try to estimate what's happening in zip code, you will start from scratch as if you didn't have any knowledge. But one thing that we can use is to use Bayesian framework to, when we try to estimate what is happening in zip code, we're going to use what we already identified in the surrounding zip codes and that's a way to be a little bit more efficient, just because of the small numbers. So we really want to do not waste any data. So this is just like to give you the intuition, the motivation about why we use this approach. So at the end of the day, we get for each zip code an estimate of the area I for a given set of definitions, and we also get a standard error, which is hopefully optimized. And it's, even if there is no autocorrelation, it's not harmful. In the worst case scenario, you get the same. So that happens sometimes. You don't have a lot of spatial autocorrelation, or so using the information for the surrounding zip code doesn't really help, but it's not a big deal. So on the left, this is some of the main results. So you can just see, just like you have, just like on a y-axis, this is area, right? So the quantification of the deviation from additivity or the additive interaction. So you can see that you have a different threshold of wildfire. You have this kind of dose response. So of course there is this synergistic effect, which is just like at the state level. But then what we did, and you can see the first map is a spatial distribution of the area, right, at the zip code level. And you can see a lot of heterogeneity. So you also have some zip codes in which actually you have a protective or less than the sum of both effect. And on the right, this is what we call a truncated signal to noise ratio, which is just one way to map, visualize zip code specific estimate that will be particularly statistically precise. So using this zip code specific area array, we also conducted a random effect meta-regression to try to understand what type of factors were driving this spatial heterogeneity in terms of the synergistic impact between extreme heat and wildfire. And this is what we found with, for example, I don't know, let's take an example like, yeah, for example, if we focus on like the percentage of people self-reporting being Hispanic, you see that the synergistic impact increases by a specific amount. And this is just to understand what is driving this, like this synergistic impact. So yeah, just another example about what you are trying to do to understand how, like the complexity and heterogeneity of wildfire smoke in the context of heat.
Just to make sure I understood this. So those that are above the zero, it means that, for example, Hispanics are in the other one, population density. It means that for one IQR increase in those, there is that increase in the RI, which means there is more synergistic effects. While everything below the line, like per capita income or percent Y, it means there is more antagonistic effect. Maybe.
It's when
they don't synergize.
They don't. It's not
that
synergistic.
the effect, that the sum of their effects
it's less than the individual.
Okay.
Well, it's not necessarily antagonistic, it's just not as synergistic.
They don't cancel each other. This is just not as high as the sum of both.
Because the overall is positive. The overall positive, meaning that the negative ones are less synergistic.
So I think we can, if you have any question before, because the next slide is a paper. I have 15 minutes, more or less. Okay, so the last paper I wanted to show, something it's paper that we are still working on. So any suggestion or comment is welcome because it's not too late. But here, this is also an opportunity, a pretext I wanted to just to take to discuss about how we can use all of the family of quasi-experimental methods that are based or capitalize on the timing of a natural experiment to study all of these climate hazards. Because as soon as you can think about climate-sensitive exposure, such as wildfire event, wildfire smoke event, as soon as you can justify that the timing of when the smoke is going to a specific place is random or independent from like the health outcome of interest or the trend itself health outcome of interest, this is a perfect setting to capitalize on the natural experiment. And this is the case for many climate-sensitive exposure at the end of the day. And so here the idea is to try to see how we can just like use this idea to try to understand the spatial and temporal heterogeneity of a given climate-sensitive exposure. Here I'm talking about wildfire, but what I'm going to say about wildfire works very well for extreme heat, works very well for hurricanes, or for any types of events that for which you can make a good justification that the timing is kind of independent from like the trends in a health outcome of interest that you can study. So and here I'm just going to, so this is based on all of this literature that I don't know if you saw or not, but all of this kind of Santa Ana, Galloway extension of just like adaptation to staggered interventions. So it works very well when you have, I will talk about that actually in a few slides, but it works very well when you have like one policy that is implemented in different, or one natural experiment that could be a policy or wildfire event that is implemented in different locations at different time periods, for example. So using the traditional or canonical different diff is going to fail for obvious reasons, because, for example, there will be some heterogeneity of the effect depending on when the policy is infected. You can't use like you can't assume that treated unit that can be used as a control before, because there is like there are a lot of independence assumption are going to violate, etc. So this is why in the last 5 years there was like many papers about we should not use the canonical definitive for this situation, etc. So here the idea is to adopt that in the context of a generalized synthetic control, and I will explain how it works, at least the intuition, to study this kind of climate-sensitive exposure heterogeneity. And today I will just show over space, but you can do that for both over space, over time, etc. So this is just like why I think, and I think it's important to understand this kind of sources of heterogeneity to try to have some kind of adaptive warning systems, for example. So before, just to give you a very brief overview about natural experiment. So just about terminology, we talk about natural experiment as a situation we capitalize on. So usually we have two families of natural experiment. We have the natural experiments that are based on eligibility criteria. So most of the time in this setting, we're going to use instrumental variable methods, including regression discontinuity. So for example, you want to evaluate the effectiveness of a vaccination, you can capitalize on people above a specific age are going to be eligible as people not just under the age are not going to be eligible. So you can capitalize on that. Many people did that for COVID vaccination, for example, etc. But then you have another family of natural experiments which are based on the timing. So for example, when a policy is implemented at a given time, if you can justify that the timing is quite random, if they didn't implement this policy at this specific time because there was a huge increase in I don't know, like the incidence of a specific outcome of interest, if they implement the policy following that, which was the case, for example, in relation to COVID, the lockdowns, there was a lot of discussion about that. If the lockdown were not independent of the outcome of interest because it was actually implemented because there was an increase in the number of rates. So that is not a very good natural experiment. There are many interesting papers about that. Anyway. So this is a second type of natural experiments that we can capitalize on if it's based on the timing of intervention. And depending on how we capitalize on a natural experiment, we can use what we call quasi-experimental methods. And the goal of these quasi-experimental methods are to help capitalizing on that and to deal partially with unmeasured confounders. The main motivation for using quasi-experimental methods is really to deal with unmeasured confounders. So when we focus on these types of quasi-experimental methods that are based on the timing of a natural experiment, there are different assumptions to think about the parallel trend in a canonical setting, about what happens when you have time-varying confounders, what happens when you have multiple treatments, etc. And you have like a kind of a series of methods. Starting from if you don't have a control group, you can think about interrupted time space analysis. But if you had like a control group, it would be the family of diff in diff, difference in differences. And then you can, if you have multiple control groups, you can couple diff in diff with propensity methods, but then you can think about synthetic control methods. All of that, they do the same thing, just like different comparison. And in the synthetic control methods, you have extension, including the generalized synthetic control method. So here, this is just a simulation we did. So this paper was published last year, I think, or a few months ago. It took us 4 years to get published, so I don't even know when, but it was a very huge effort. But we wanted to do a comprehensive. So first, it's a big tutorial, just so we explain like how, like the intuition behind all of these methods. And then we did a simulation to see how these methods perform in different settings when you violate the parallel trend assumption, when you have multiple control groups, when you have a lot of time complex time structures, etc. We have all of the codes if you're interested by this method. So yeah, if you're interested, that could be practical. But here, this is just very quickly, just like this is one of the results of the simulation. And here, overall, we compared, you can see the traditional synthetic control method, the one proposed by Abadi. We compared interrupted time series analysis, generalized synthetic control method, diff in diff, or controlled interrupted time series analysis, which is the same thing at the end of the day. And here, what we found basically is that when you have the opportunity to use control groups, it's the safest approach is to use the generalized synthetic control, which is a data adaptive method. So if you have the choice, generalized synthetic control method will always outperform any other method. So this is just what we found in the simulation. Other papers propose the same thing. So here this is just a simulation showing that actually it works better when you can, because if you need enough control groups and enough predictors to try to have the generalized synthetic control method work. But if you have that, this is systematically outperforming other methods. So this is just to explain why I'm going to talk about generalized synthetic control method. So again, this is a method that has been proposed as an extension of the canonical synthetic control method in 2017 by a political scientist who used to be at UCSD and now is at Stanford. And the idea, just to give you an intuition about how it works. So let's say you have multiple treated units, or just for the one treated unit. So you have one, for example, county or zip code that is exposed to a specific policy or a specific shock or wildfire. So, and then you have a set of control zip codes, for example, that are not exposed to the wildfire. So the idea is that you're going to try to, so you have multiple time series. So you have a time series for the treated group. So you have a time series for the outcome of interest, but also for the event, like potential time-varying covariates. That could be temperature, lag temperature, could be like total PM 2.5, etc. Could be any types of time-varying confounder. Then you have the same thing for the control units, the control zip codes that were not exposed to the wildfire, for example. So the idea is that separately, you're going to decompose the time series. So you're going to try to understand how like the time series can be decomposed according to the lag of the outcome of interest or the time varying covariates. And then you're going to summarize how these variables explain the trends or the time series in a given outcome of interest, for example, the daily rate of respiratory hospital admission. And it will be the equivalent, you get these latent factors. Latent factors is the equivalent of doing a PCA. So you just try to understand how, just like, this is like what the equivalent in a PCA will be an eigenvalue. So to which extent a variable helps explaining just like how like the variable explains the variability in your sample. So here, this is something that applies to a time series. So you will have in a treated group, like an information about how each of the predictors contribute to explain the time trends for the given outcome of interest. That could be respiratory hospital admission. So you're going to do that in a treated group, and you're going to do that for each of the control groups. And then what you're going to do is just going to compare how these latent factors are going to compare between the treated and the set of control units. And you're just going to apply a weighting procedure. You're just going to give more weights to the control units at a given time point that have a very similar latent factor, and vice versa. If like you have a latent factor that is very different, you're just going to give it very slow, like low weight, etc. And then by doing that, you can build like a synthetic control, which will be like a non-existing zip code that is a weighted combination of all of the unexposed zip codes that will be mimicking the trend of the outcome of interest as best as possible. And this is just like, again, very intuitively, but this is the idea of the generalized synthetic control method. And yeah, so it has not been developed for this type of situation, but here we just like the point was just to show how we can actually use that for wildfire, but any type of climate sensitive exposure, as soon as you can argue that the timing is random and you can capitalize on a specific climate sensitive exposure as a natural experiment. So that being said, so this is just an example about one wildfire event in 2007, and you can see here, like you have the red zip codes that were exposed to the fire, and the blue one, the one that were not exposed, that was eligible to be controlled. And for each of the treated zip codes, we did this procedure, and you can see here on the right an average of the, just like you see in black, the exposed zip codes, and in blue the synthetic unexposed. So this is just like to mimic what would have happened in absence of the smoke. And then during the smoke event, you just compare what happened to what would have happened using synthetic control estimates. So this is the same interpretation as traditional canonical synthetic control, but this is just one way to do that. So that is for one event. So so the idea, what I was saying before, is that you have all of this extension of this when you have multi-treated setting, or when you have staggered intervention. For example, when you have wildfire that will impact multiple units, but it doesn't come at the same day. For example, it starts on a Monday in New York, but then on Wednesday it comes to Philadelphia, etc. So you want to study that, and one way to, this is a staggered intervention setting typically. So you don't want to use a traditional method, and this is what this literature has focused on. So, and the idea is, you will see it's way more simple than it seems when you read the paper, but econometric paper, just like they want to be, I don't know, it's sometimes overly complex for no reason, but the idea is really that you just have a two-stage. So you estimate for each event or each like a treated unit separately, and you just like need to carefully select the control units. So you just need to be careful, but this is feasible. And then you just meta-analyze that to get a pooled effect estimate. And that is what they propose, like Galloway Santana, this is what they propose in the context of a definitive. So we can easily extend that to a generalized synthetic control. This is what we did. And then one thing that you can do is just to also couple that with try to understand if you have some variability in the ATT, so average treatment effect among the treated, you can try to, same thing as I presented before, try to understand like what is driving that. So what is driving the heterogeneity of the ATT, and just try to understand that. And that could be over space or over time. It's that's just like a summary of what these new methods are doing. This is just like to try to decompose that into stages, to try to treat correctly when like a policy or natural experiment happens, and which are the eligible control at a given time point for specific treated units, and to try to deal with that correctly. So that's so we just simply adapted that to the generalized sensitivity control method, and here we just focus on the 2018 campfire approach. So here, this is just like before the fire and during the fire. So we were able, using the wildfire, like wildfire smoke PM2.5 data, know which counties were exposed to the fire. So we were able to assign 25 counties exposed to this specific campfire during like November 8 and 14. And so what we did very simply is we just analyze for each county. We analyze like the estimated ATT to quantify the specific effect estimate of the wildfire smoke event. So on respiratory hospital admission. And then we had a distribution of ATT across these 25 counties. And one thing that we try to do is disappointing, the results are disappointing, but this is try to understand like what characteristic may modulate that. But the idea of this approach is to show how we can apply that spatially and temporally, because you can also have like multiple wildfires, and you can try to understand why sometimes the wildfire effect is going to be larger. Is it because it's hotter? Is it because there is a lot of background air pollution? Is it because whatever? So you can, this is something that could be helpful to answer many types of questions. So, so this is just an example. So we just replicated that, but we carefully selected for each county, just like what would be eligible control counties, and we estimated the ATT just for each county of interest. So here you can see that, for example, for San Joaquin County, you can see that the difference before the wildfire started, the difference between the rate of hospital admission in San Joaquin as compared to the built synthetic control, it was close to zero, which is what we need. And then we see that there is an increase, which we can use to estimate ATT. And what we do typically is just to calculate a kind of an average across multiple days. But you can actually get a daily estimate if you want to. And here you can see the Santa Clara, Alameda. So we did that, but I think I have all of them here. So here we have all of the 25 counties that were exposed to the fire, and you can see that there is a lot of heterogeneity across the counties. And one idea is to try to understand what is driving this heterogeneity. Why, for the same event, why people were super impacted in, for example, Sacramento, but in the Napa Valley, the ATT was relatively small also. So this is just like the type of question where this approach is trying to address. But this is just an application. The paper is really about how, like, the rationale for this method, but then it can be applied for trying to understand spatial heterogeneity, but it could be useful over time, specifically to understand the compounded impact, or try to understand like the duration of the fire, try to understand many things. So, and again, that is about wildfire, but that could work for any types of climate sensitive exposure at the end of the day. We did that just for the proxy, but it's a little bit disappointing because this is just to try to understand if there is any of these variables that we had already had collected that could explain that, but not really. But that's okay. This is just like the motivation was to explain how we can do that in many different settings. So I think this is it. So thank you. And I'm
Yeah, something on the generalized synthetic control, just to make sure I got it.
You want me to go back?
Sure. So What's the difference between this and a control ITS?
So
Intuitively.
yeah, so control ITS. So control ITS, there is like, so it's coming from two different fields, but control ITS is exactly the same thing as diff. So, and the way it depends how you fit your control interpreted time series analysis, because if you fit your control, like your interpreted time series analysis with a control group, you can, if you have one control group, that will be like a canonical diff, and you run one model with two fixed effects and an interaction between the two fixed effects. This is what a control ITS does. If you have multiple control groups, then you can use a control ITS that, and you can, just to make sure that the control are going to mimic that, you can use IPTW, for example, and that will be very close to a synthetic control group. But it depends how you use the control. ITS is just a generic term that, depending on what you're going to do, this is like general synthetic control is one way to deal with a controlled, interrupted time series analysis, but control interrupted time series analysis is just using specific field that it's confusing because it's exactly the same as the diff family. To me, all of these methods are the diff family. And so just sometimes you have one control group, some have many points before the intervention, sometimes not, etc. So this is just like a spectrum.
Yeah.
But yeah. But yeah, that's a control interrupted time series analysis setting, and we use this approach to deal with it.
Okay.
Yeah.
So in that last slide that you were showing, so are you just taking the predicted?
Which one?
Oh, the very last one, I think
Ah.
it's looking at yeah.
This one?
So are you using the predicted effect ATPs for each
County.
place,
Yeah.
county?
Yeah.
And then you're just saying you and you.
Yeah. Exactly, just like, yeah, but again, this is, but yeah, but we can, here, this is just for one fire event, but we can also try to see if, let's say, we have multiple, like 20 years of wildfires, and we can just get as many ATT as fires and zip codes or county of interest, and then we can try to, like, for each of these ATT, we can assign a vector of information. It could be just like the quantity of smoke or smoke PM2.5, can be the season, it can be the temperature, etc. And in the second stage, all of these characteristics that you assign to a specific fire event, you can try to see if they explain the variability of it.
So is that assigning it to the treatment variable, or are you assigning it as a covariant?
So in the first stage, you just like, in the first stage, you treat each event separately.
Yeah.
So, and for each event, you build a different synthetic control. So you estimate for each event or each event and spatial unit, ATT. So for the ATT, that is specific to a spatial unit and a specific event, you can assign as many characteristics as you want that are specific to this event. And in the second stage, once you have like a distribution of ATT across space and time, you can try to see if these characteristics explain the variability. And this is what we talked about this morning about do that. We can also do that in a mixture setting. If you want to consider if they are super correlated, also you can apply whatever weighted quantile sum or quantile G computation or anything. Or BKMR, but this is I'm not using it because I don't understand it.
Yeah.
So, but yeah, does it make sense? Yeah.
Well, I think we're actually a little over time.
Okay.
So I don't know if folks have any burning questions. And if not, maybe we'll say thank you so much. That was super interesting. I wrote down a lot of stuff, so.
And I'm happy to share the slides. So the papers are not published yet, so but I don't know what, even if you're really not well intentioned, I don't know what you can do. I'm happy to share the slides.
Thanks.
So thank you. Like close?
I don't know what all those, there were a lot of chat.
I think it's not the recording. It was mostly me asking people like, does it sound okay?
Okay.
Quiet, like, it's a mic.
Oh, where is that?
That
Oh,
one.
yeah.